Welcome to part 1 of the Unit 2 Chemistry Edexcel IAS specification revision. Unit 2 is essentially composed of energetics, group chemistry, halogenoalkanes. Sorry, my pen wasn't working. Energetics, group chemistry, halogenoalkanes, and alcohols. Okay. So, to start off, we can start off with, again, it's a 90-minute paper. It's composed of 80 marks. But yeah, let's begin. 3 sections by the way, so multiple choice, then the 2 long sections. But yeah, starting off with topic 6, energetics. So very quickly, 6.1, know that enthalpy change is the heat change measured at constant pressure at under standard conditions of 100 kilopascals and a specified temperature, usually 298 Kelvin. So enthalpy change is basically it's written here. It's the energy change measured at constant conditions. Okay. So when a reaction occurs, uh, NaBr plus Cl2, you'll form NaCl plus Br2. Okay. In this reaction, there will be a change in heat. Why is there a change in heat? Because there is energy required to break these bonds, and then there's energy released when this bond is formed, okay? To break even this bond here, to break it into 2 different Cls, to break this, and to form these bonds here as well, okay? So, delta H can be represented as energy, energy required to break bonds plus energy to make bonds. Now, it's important to note that energy required to break the bonds is positive, delta positive, whilst the energy required to make the bonds is delta negative. What do you mean by this? This is endothermic, this is exothermic. So, to break the bonds, you will need to take in energy, okay? It cannot just break. You need to take in the energy, and then this bond will break, okay? And to make the bond, you need to, energy will be released, okay? A way of thinking about this section is, if you have 2 steel rods and you want to combine them into one long rod, okay? How do you do this? Think of it like as you push the rod closer and closer, the air space inside will be removed. Now, instead of thinking about this with rods, think about this with elements, okay? Let's have Na and let's have Cl. As you try and combine these elements, the energy in the middle will be released, okay? So be released, hence it is exothermic and negative, okay? It's important to note that. But yeah, that's just my way of trying to remember what bond is, if energy to make bonds is negative or positive, okay? Remember it's negative because it's exothermic. That's basically that. So, and then we have to note that enthalpy change is always done under standard conditions of 1 atmosphere pressure, which is equivalent to 100 kilopascals, and room temperature, which is 25 degrees Celsius or 298 Kelvin. Remember, 25 degrees Celsius, when you add 273, you get 298 Kelvin, okay? Conversion to Kelvin is basically just adding 273. Now, we can tick that. Next part, know that by convention, exothermic reactions have negative enthalpy change and endothermic have positive enthalpy change. We talked about this. Exothermic reactions, they will result to a negative enthalpy change, and endothermic is positive enthalpy change, okay? So we can tick that. Be able to construct the enthalpy level diagram showing exothermic and endothermic reactions. Okay. When you're drawing energy level diagrams, ELD, you do not call it ELD, but I'm calling it that to save on time. When you have endothermic energy level diagrams, when you're supposed to draw it, okay, you'll have energy here and time on this axis, time for the reaction to like move on, okay? Let me write that better. Yeah, so remember reactants here. This is the reactants. Let me actually put this in the middle. Reactants. And again, like we said, endothermic reactions, the delta H, the enthalpy change is always positive, okay? So positive is always in the upward direction. So we'll move up and then products. Now, we can extend this line using a dotted line. Here to here is the delta H, and as we can see, it's an increase, so it is positive, okay? But what is the activation energy? The activation energy is the energy of the product, the reactants, to the total energy required to make the reaction occur. So it's from there to there, and it's represented by EA, which stands for activation energy, okay? For exothermic reactions, it's a bit different. You'll have the same axes, if that's a word. Energy will be here, and time, or the reaction progression time, will be here. And again, reactants. And here it's a bit different. The total enthalpy change is negative. So it'll be here, the products. The energy of the products will be less than that of the reactants. So you can have a dotted line. But we cannot just combine it like this. Remember, every reaction has a certain energy required. Most reactions have energy required for them to occur, okay? So it has to go slightly up and then down. The activation energy is not this. Remember, it's always from the reactants. So let me draw that better. It's always from the reactants. So it'll be like this. This is the activation energy represented by EA, okay? Big E, the capital E, and small undercased, lowercase a. Okay, yeah, so that's how to construct those diagrams, so we can take that. Next up, know how to define standard enthalpy change of all of those, okay? So, how do we define all of this? It's very simple, actually. All we need to know is, what is standard enthalpy change? It's 1 mole of something being done under standard conditions. Okay? Now, every explanation will have this, but depending on whether it's reaction, formation, combustion, neutralization, or atomization, this part will change, okay? So under standard conditions, and we have to list of what? Of 1 atmosphere pressure, which is 100 kilopascals. Sorry, which is 100 kilopascals, and you have to mention and 298 Kelvin. You can't say room temperature, you have to list the actual amount, which is 298 Kelvin, or 25 degrees Celsius. Okay, so which is which now? Enthalpy change of reaction is essentially the enthalpy change when it's defined as the enthalpy change when quantities of substances in standard states react to form 1 mole of a substance, okay? How do we define this? This is basically when 1 mole of, a better way to say this is, enthalpy change of reaction is when, it's when 1 mole reacts with 1 mole of something and you form a product, okay? This is the enthalpy change of reaction, okay? So a way to say it in actual words is, it is the enthalpy change when 1 mole of a reactant reacts with 1 mole of another reactant under standard conditions of, and then you see all of this, okay? So yeah. Now that is a reaction done. For formation, it is the enthalpy change when 1 mole of a substance is produced from its elements under standard conditions, okay? What do you mean by this? Basically, just look at the word formation and you say it's when 1 mole is formed under standard conditions. But you also have to mention that the elements that it's formed from are under standard conditions, okay? Under their actual states. So if it's hydrogen, it is at gas. If it is mercury, it is also at gas, okay? If it is sodium, it is at solid. So we have to know that, okay? That's for formation. For combustion, it is the enthalpy change when 1 mole of a substance is completely reacted with oxygen, okay? So again, 1 mole of a substance reacts completely with oxygen. If you don't want to say reacts completely with oxygen, say it's completely burnt in oxygen, okay? That's for combustion. For neutralization, it is defined as the enthalpy change of a solution when an acid and an alkali react together to produce 1 mole of water under standard conditions, okay? So it's acid plus alkali to produce 1 mole of water. Also, it produces a salt, but we're not looking at the salt, we're looking at the water, okay? Yes. One second. Yeah, so again, I just want to go back on something. I had made a mistake on the reaction part. The actual way to define the reaction is, as we can see, delta HR. This will just be equals to delta H. So my previous definition was a bit incorrect. It's quite honestly what we talked about before. Let me go here. Yeah, this delta H for this reaction is just delta H reaction, okay? That's what we're supposed to know. So the delta H for a reaction is when the energy of the products is minused with the energy of the reactant, okay? Sorry for the misdefinition before, but yeah, that's how you define that, okay? Now, lastly, enthalpy change of atomization. It's defined as the enthalpy change when 1 mole of a gaseous atom is formed under its standard state, okay? Or an element from its standard state. What do we mean by this? When you have sodium, it's a solid at its standard state, yeah? So to convert it into a gas, to convert it to 1 mole of a gas from 1 mole of its actual state, the enthalpy change under standard conditions is known as enthalpy change of atomization, okay? So for all of this, it's basically just 1 mole and standard conditions. If you list that itself, you'll get 1 mark out of the 2, okay? But to get the other mark, we need to look at these words, okay? If it's a reaction, just know it's product minus reactants, but reaction is not tested as much because it's just known as delta H. So they'll tell you to do calculations. But to define, they'll give the other 4, okay? Formation is when 1 mole is formed from its standard elements. Combustion is when 1 mole is burnt completely in oxygen. Neutralization is when 1 mole of water is formed from acid and alkali. And atomization is when 1 mole of gaseous atoms is formed from normal state atoms, okay? That's what we need to know for that. So we can just erase all of this and tick this because we're done with it. Next up, be able to use experimental data to calculate energy transferred in a reaction using this equation. Okay. O-level physics, we had a reaction that was E is equals to mc delta T, okay? Yeah, so we do know this reaction. This is the energy for C is the specific heat capacity of something, okay? M is the mass, and change in temperature is the change in temperature. Well, yeah. Change in temperature can be in degrees or Celsius because it's both the same thing when you're changed. Like if you have 25 degrees and you increase it to 30 degrees, this is to 98 Kelvin, and this is 303 Kelvin. So the difference will be 5 on each side, so it doesn't matter which one you use. But for the others, mass has to be in kilograms, and specific heat capacity, they give you the units usually, so just use that, okay? Now, this is just O-level stuff, but the difference here is they will give you a reaction, okay? Copper reacting with sulfate, okay? You form copper to sulfate, okay? They tell you 3 grams of copper has been used. Find the specific heat capacity, sorry, find the enthalpy change, find the specific enthalpy change to this reaction, okay? What will you do? You will find E is equals to mc delta T. They'll tell you the change in temperature is equals to, like, let's say 10 degrees Celsius, and they will give you C as 2, okay? Let's say C is 2, the specific heat capacity of the solution is 2, okay? You will essentially convert this to kg, so it'll be 3 divided by 1000 to get 0.003 kg. And you will put these, you'll plug these values into the equation. You get 0.003 times 10 times 2. This will give you 0.03 times 2, which is 0.06. Okay, this is your E, but this is not your specific change in, this is not your specific energy used, okay? This is not the enthalpy change of the reaction specific to the heat. What we do is, we take this E and we have to find the moles of the copper. I don't know why it's using that. We have to find the moles of the copper, okay? Now, we essentially just go and we find, how do we find the moles of copper? Copper, the moles is equals to the mass over the RAM. You find the moles, you plug this 3 grams here. You do not convert it now, you plug it in as grams, and you plug in the RAM, and you get the moles. So, let's say we got 0.003 moles. This is just a hypothetical value. We're not actually getting it. Okay, let's use a different number. Let's say we get a 0.45 moles, okay? We wouldn't get this value if we actually calculate it, but let's say we do get it. We write 0.45 moles of copper gives us a change of enthalpy of 0.06. What does 1 mole give? And we cross multiply, and we will get our energy of our standard enthalpy change of the reaction, okay? Whenever you have standard enthalpy change, note that it's always 1 mole, so you have to use this method to get that energy value. You cannot use the energy that you get here, because that is incorrect. You lose 2 marks there, okay? So that's how we use this equation in an A level, in a differential way that is in A level compared to O levels, okay? Know Hess's law, be able to apply it to constructing enthalpy cycles. Okay, so what is Hess's law? Wait, did I miss something? Yes, okay. Calorimeter, I missed this. So, a calorimetry is essentially an experimental method to find the enthalpy change of the change by measuring temperature change over time, okay? If you have a graph, this came in my exam last year, so it's best that we, note this actually. If you have a graph of temperature against time, and you're an experimenter, okay, you would plot values. Initially, there's no temperature change, but then you note it down every, let's say, 30 seconds, okay? 30 seconds. But then when you add the metal is added here, okay? Let's say the metal is added at temperature of, wait, let's just do this at a better way, okay? More accurate way. These are the divisions, okay? Subdivisions. Now, when you have, you plot at each time, and the temperature is always the same, okay? This is 0 seconds, this is 30 seconds, 60 seconds, 90 seconds, and so on, okay? Let me not say so on, let me just write it, actually. 120, 150, 180, and 210, okay? And you add the metal. Let's say this is an acid reaction to a metal, okay? And you have a thermometer there, okay? Let's just draw this. You have a acid, you have a thermometer, and you add your metal, okay? You add the metal inside. At time is equals to 100 seconds. That'll be over here, okay? But then we measure at 120 in intervals of 30 seconds. The temperature changes over here. And as you keep going, there's a decrease in temperature. What we do is we draw lines of best fit, like this, and at temperature of 100, at time is equals to 100, we draw a line and we extrapolate and we find this value. This is the temperature that we will use. So when you're finding the change in temperature, you do not use this temperature here. Instead, you have to extrapolate by adding a line and then corresponding it with the time the metal was added, and then finding this temperature change now, okay? And you'll use this delta H into your equation, MC delta T, sorry. You'll use this, sorry, this is delta T. So you'll use this delta T into the equation, E is equals to MC delta T. If you use this value, this temperature change, you will lose quite a lot of marks, okay? This did come in my exam and it can come in your unit 3 as well, so just keep a note of it, okay? So yeah, know Hess's law and be able to apply it to constructing enthalpy changes, calculate enthalpy changes of reactions using data provided or data selected. Okay, so Hess's law. What is Hess's law? Hess's law is defined as when you have, let me just draw this like this, okay? When you have three compounds, okay, A, B, C. A reacts to B and B reacts to C. Sometimes you cannot directly calculate the enthalpy change from A to C. So you have to look at the enthalpy change from A to B and then B to C, okay? So we cannot do this. This doesn't work. So instead, we use an alternate route, which is what Hess's law is. It's using an alternate route to find the enthalpy change of a reaction, okay? So you go from A to B, you find that enthalpy change, and you add it to this enthalpy change to get the total enthalpy change from A to C, okay? That's essentially what enthalpy change of using Hess's law is. But yeah, now it's important to note that if the arrows are changing, let's say the arrow is not from there to there, it's from here to here, and you want to find delta H, you will use delta H1, which is this, and this is delta H2. So you'll do delta H is equals to delta H1, follow the direction of the arrow. It is positive direction, it's not going backwards, so we'll do it positively. You add it to this one, but this arrow is going in the opposite direction, so you will subtract delta H2, okay? It's vectors, and I think this was done in O levels as well, but yeah, in maths in O levels, but yeah, basically just vectors here. That's how we use Hess's law to do this stuff. So you can take that. Okay, in the next video, we'll complete topic 6 and begin topic 7, intermolecular forces.